All right, everybody, welcome back. We're going to continue with our review of measure theory. We're almost done. We've got two more videos after this. One more video on measure theory, and then we've got one video on complex analysis, and then we'll be done. We'll be starting the first chapter of the book. So we've talked about a measure, what that is. We've talked about a Lebesgue measure, what that is. Now we need to talk about, given a measure, how can I integrate over that? So if you remember way back a few videos ago, I was talking about, redefining this notion of length to be more general, given a measure. And if you think about what you're doing in an integral, right, summing up those little rectangles, this is a very loose way of looking at things, but I just want to give you an idea. We take the area of these rectangles, and what's the area of a rectangle? It's base times height. Well, in the case of integrating a function, your height is what? It's just going to be the value of the function at some point, if you want your rectangle to be on the left or the right or centered, whatever you want. And then the length of that rectangle, right, is that length on the x-axis. But this whole measure idea was to redefine this notion of length to be, well, not maybe redefine it, but expand it to be whatever you want. And that what you want it to be is defined by the measure you have. And so that base length of the rectangle will be the measure of, let's say the base runs from x is equal to 1 to x is equal to 2. Well, then the length will be the measure of the closed interval, with endpoints 1 and 2. Okay, so that's looking ahead. But to define the Lebesgue integral, we need to first define it for perhaps one of the most basic classes of functions. And those are simple functions. Just like the name, they're very simple. The image you want to have in your head of these is a step function, is a bounded step function. Okay? So what is a simple function? We'll take any non-empty set x and take any finite amount of real numbers, alpha 1, alpha 2, alpha n. Okay, these are going to be the values of your simple function. That's all a simple function is. It is a function on a set x that takes on a finite number of points in R. Its range is just a finite number of real numbers. That's all it is. Let's look at some important examples of step functions you might already know. The first is perhaps maybe look at some examples of simple functions. The first is probably the simplest among the simple functions. It's called the characteristic function. And all the characteristic function does is it tells you whether or not you're in a set. So take x to be any set, assume non-empty, avoid the trivial case, and take a to be any subset of x. The characteristic function, which I denote chi a over a, is given by the following. Take an x from the space x. Chi a evaluated at x is going to depend on whether or not x is an element of A or not. If x is in A, chi of A returns 1. Chi a of x returns 1. If x is not in A, then chi a of x returns 0. Right? It's just basically telling you whether or not x is in the set A that appears here in the subscript. This is an example of a simple function. If you want to draw it, we can go ahead and do a picture. Otherwise, this whiteboard here is not serving its purpose. So take A, think of a set. We'll say 2, 3, union with, let's make it interesting, and do 4. Okay? Draw chi A. That's what we're going to do. Well, the first thing I do want to say is, notice it's, notice it's a simple function. Why? What are the values that chi of A takes on? Okay, it's just two values. It'll either map an element to 0 or 1. So you can view chi A as a mapping, we'll say, from the non-negative real numbers over to the set 0, 1. And that goes for any set A that we choose. Now to draw it, I'm just going to follow this definition. Okay, Let's see. We'll draw it in blue. Well, starting, oh, there should be a 0 there. There we go. Well, starting at 0, well, 0 is not in the set. So chi a of 0 is going to be 0. And it's going to continue being 0. Every element between 0 and 2, not including 2, are going to be 0. So let's say that's 2. Well, chi of 2 is 1. So we'll go up here and say that's 1. Chi of 2 is 1. Okay. And for all x between 2 and 3, well, by definition, x is an a. So every x between 2 and 3 inclusive will be mapped to 1 under the characteristic function. So it's going to look like this. Until we get to 3. Let's draw dotted lines. Say this is 3. We drop back down. Okay. And then everything between 3 and 4, not including the endpoints, is not an a, right? By just how we defined a. Very simple. So those will map to 0. So between 3 and 4, characteristic function is 0. And then boom, once we hit 4, it's equal to 1, but just at 4, nothing around it. And it'll go back down to 0. And it'll keep going that way off to positive infinity. All right, it's very simple. Now, why bring up the characteristic function now? Well, as it turns out, you can actually view every simple function as a linear combination of characteristic functions. That means, what does that mean? Well, let's see. I'm going to start with a characteristic function s, going from x to some finite number of real numbers. Okay, well, let me define a sub j as the preimage of alpha j under S. Okay, so aj is everything in X that maps to the real number alpha j. Okay, so watch this. I'm just going to write S as the sum from j going from 1 to n of alpha j, where each term of the sum is alpha j times the characteristic function of aj evaluated at x. Right? This is a constant, and now this is a function. So we have written S as the linear combination of functions. Those functions are characteristic functions. Okay. I don't know if this is obvious. Maybe you're not convinced by it. If you look, like let's look at where, pick let's say, say we have some element of x that maps to a sub I, and I is between 1 and n. Okay. Let's verify that this definition, we'll say s tilde, it gives us the same, this function s tilde is the same as s, right? Okay. So we know that s of y is equal to alpha I. We want to see if that's the same for s tilde. We'll just look at it. So since s of y is equal to ai, well, guess what? Y is in the preimage of alpha I, which we defined to be it's in the preimage of alpha I, which we defined to be a sub I. Now, because s is a function, right, it's well defined, y will not be the element of the preimage of any other of these alphas, right? So it will only be in the set a sub I. Okay, now what does that mean? Well, if you look at the sum right here, the characteristic function of a sub j for any index j between 1 and n, that's going to, evaluated at y, that's going to be 0, okay, unless y is in the subscript set. But the only subscript set, this is what I mean by that, is the only aj that alpha is in is for j is equal to I. Okay, so the only non-zero term in this summation is when my index is equal to I. So then that means that s is equal to s of y is equal to alpha I times chi ai y. And since y is an ai, that's just 1. Okay. It's an awful 1, but there we go. All right, that's a little bit better, which is alpha I. Okay, so it's the exact same thing, but we've written it as a linear combination of characteristic functions, which is sometimes helpful to do. Okay. One thing to keep in mind is that this expression, you can actually go in the reverse when you define characteristic functions. And, we went from this definition to this linear combo of characteristic functions. You can actually just define characteristic functions. You can define simple functions. Oh, I might have mixed those terms up, so be careful for the last minute. I'm sorry about that. You can define simple functions strictly in terms of characteristic functions. Give me a partition of x, okay, or whatever set you want to define the simple function over. Okay, give me a partition. What is a partition? That is a collection of subsets of your domain, okay, that are disjoint from one another and whose union is the entire domain. And then all you do is you consider every element of the partition. And since this only takes a finite number of points, make sure you define your partition so that, every partition element uniquely corresponds to which value your simple function takes on. Okay. So this is exactly what we did here. You just take your partition to be the preimage of your simple function under one of the alphas, the points that it maps to. Okay, and then you just write the linear combination. You have the characteristic function and then you have its respective weight. Okay, very simple. So you can define simple functions that way. Now, a more specific example, and this one's going to kind of be part of a theme throughout this lecture and the next one, because I want to keep coming back to it. It's really, it's going to illustrate actually a good amount of concepts here. So, and this is more particular. Don't be scared by this formula here. Everything's going to be okay. Okay, everything's going to be all right. Just don't be intimidated by this. Okay, we're going to take x to be the unit interval, subset of the real line, and f to be equal to x squared, define over the unit interval. We're restricting our attention for x between 0 and 1 inclusive. And I'm going to be defining a sub n of x, a for approximation, like this. Okay, now this is a lot, but something to notice is, ask yourself the question, is it a step function? And because of what I was talking about earlier, because you can see this is a linear combination of characteristic functions, right? It's a step function, and it takes on only it's a finite linear combination of step functions. I should always specify finite, right? Well, it just needs to take on finitely many values, and your cases are going to reduce. If it only takes on finitely many values, it's going to reduce to, you can simplify things to a finite sum. Okay. But anyway, you can see obviously from this, well, I shouldn't say obviously. You can see from this expression, hopefully, that a sub n only takes on a finite number of values. Okay. It's going to take on 0, right? Because, the coefficient of all of these numbers here, right? This is just a number, right? We're not evaluating this at x. There's going to be some number times a characteristic function. This might be 0. All of these might be 0. Okay, so this will take on the value of 0. Okay, what other values will this take on? Well, look at the sets being defined, the sets that are in the subscripts of the characteristic function. What do? Well, what we're actually doing, what these sets form, is a partition of the unit interval. Okay, if I write this out, okay, just looking at the subscript of the characteristic function, if I write this out, if I is equal to 1, just focus here. If I is equal to 1, what is this? That's 1 minus 1 over n. That's going to be 0. 0. Okay. And then it will go to 1 over n. Okay. Now, we're only going to n minus 1. So, and what if I plug in 2? Well, I'm going to get 2 minus 1 over n. That's going to be 1 over n. Right? We could think I'm talking about each term in the sum. Okay, so this is the subscript of the characteristic function in the first term of the sum. This is the subscript of the characteristic function in the second term of the sum. Okay, and the second term, it's I is equal to 2, and so we get 2 over n. Okay, and this is going to continue, right, like this, just keep plugging in until we get to n minus 1, where we'll get, what is that? That's going to be n minus 1 over n. That's n minus 2 over n. What's my left endpoint? That'll just be n minus 1 over n. Okay, but now we can't forget about this guy over here. We have the closed interval n minus 1 over n to 1. Okay, what the purpose this term serves, right? We can't write everything under this one summation because we're always excluding the right endpoint. Okay, but we're talking about the closed interval from 0 to 1. So to include that endpoint, we're adding this extra term out here. Okay, on the right. Okay, and that last endpoint is going to be n minus 1 over n to 1. Okay, what do you notice about this? This is a partition of 0, 1. Take any two elements, take any two of these intervals. They do not intersect. They both have empty intersection. That's a closed interval right here. They both have empty intersection. And if I union all of these together, I get the closed unit interval 0, 1. Okay, so that's one thing. The second thing is, well, let's talk about the coefficients here. What am I multiplying these characteristic functions by, right? What are my weights? Well, if you pay attention to the left endpoint defined here in the subscript of my characteristic function, it is the same as evaluating f at that endpoint. So I'm saying, right, I'm defining a as on the interval from I minus 1 over n to I over n, okay, for x in this interval, a is a constant. And what is that constant? It is f evaluated at the left endpoint. Okay, and that's the same true for here. Notice how we have f evaluated at the left endpoint of the interval in the characteristic function. Okay, what is the picture? What's the picture going to be? Well, let's consider what happens when n is equal to 2. Okay, go ahead and erase this. Okay, let's just consider the case where n is equal to 2. Okay, we're going to have two terms in this summation, and we're going to have two subintervals. Okay, we're just going to have, right, this is going to be, if n is equal to 2, we have the sum from I is equal to 1 to 2 minus 1, so that's 1. So there's just one term in that summation. So let's plug in 1 for I. We're going to get f of 1 minus 1 over 2. Okay, well, that's just f of 0. So a2 of x is equal to f of 0. Okay, now what about this characteristic function? That's going to be 2 minus 1 over 2. Oh, excuse me, that's going to be 1 minus 1 over 2, right, which is 0 over 2, which is 0. So we'll have chi of 0. And my right endpoint, I is equal to 1, will be 1 over 2, so that's 1/2. Okay. That's my first term. And I said n is equal to 2. So we have I going from 1 to 2 minus 1, which is 1. So I goes from 1 to 1. We're done with this term. Now with this term, okay, well, n is equal to 2. We'll have f of 2 minus 1 over 2. That's f of 1/2. And then my characteristic function will be over a closed interval from, let's see, 2 minus 1 over 2. That's 1/2 to 1. Okay, I'm not writing evaluated at x, but keep in mind, this is a function. If you see this, you need to be evaluating it. You have to be evaluating it at a number x. Well, maybe I'll just write it for clarity. X, x. I know it's not the best, but see, you can see why I've been typing things up. It'll make things more clear. Okay, now what does the graph of A2 look like? We'll just take the plane. Okay. Let's draw x squared in blue. All right, that's as good as you're going to get for, that's not too bad. Okay. And we'll say that this is 1. Okay. So let's plug in some numbers. Okay, well, for x between 0 and 1/2, not including 1/2, what's happening? What is happening? This term is 0 because x is not in the subscript, in the set that is in the subscript of this characteristic function. So from x going from 0 to 1/2, including 0, not including 1/2, this term is 0. So we look to this term. Okay. If x is in 0 to 1/2, not including 1/2, then this is 1. So then you get f of 0 times 1. Well, f of 0, our function is x squared, and f of 0 is 0. So what this means is that for all x between 0 and 1/2, including 1/2, not including 1/2, A2 is 0. So we draw it like this. Okay. Now for x between 1/2 and 1 inclusive, this term is 1, and f of 1/2 is what? It's 1/4. I mean, I don't know. We can just say this is 1, and 1/4 is like, we'll just say down here. Okay. Is the evaluation at the left endpoint. And so you get this. And right there, you have A2. So in general, what will happen is, as we divvy up the unit interval into n subintervals, right? That's what happens when n increases. We will be approximating the curve y is equal to x squared better and better. Okay, so another, if we take n is equal to 4, I'm not going to go through all the computations, but it'll look something like this. So we'll say this is A4 in red. Okay. It'll go like this, to this, to this, circle, yeah, that should be open, yep, there we go, to this. Okay. As you continue, what will happen is these steps get finer and finer, and they approach better the shape of the parabola. Okay, so that's what this is going to do. The goal, the story that's going to be told here, is that this will actually be a means for us to compute the integral of x squared, the Lebesgue integral of x squared, using the formula for that. Okay? That's all there is to it. So, with that, I want to talk about the integral over these very simple functions we've defined. I hope you found them simple. Okay. So given a measure space, right, we have our set x, we have our sigma algebra over that, and we have our measure defined over that sigma algebra. If s, taking x to a finite, right, s is just a simple function, but we're going to specify, this is important, if s is a non-negative and measurable simple function. We're going to talk about that in a second. Okay, well, actually, we'll just pause here. What do I mean by measurable? By measurable, I mean that S inverse of each alpha j is an element of sigma, right? The preimage of each of these points is measurable for all j between 1 and n. And we'll get to a more general definition of measurable functions in a moment. But just digest this for a second, okay? We're going to be defining integrals, the Lebesgue integral, over non-negative, measurable, simple functions. You've got two conditions for your simple function there. It's non-negative and it's measurable. And what does measurable mean? It means the preimage of each of the points in the range of that simple function is measurable, or an element of the sigma algebra. Okay? In this case, we define the integral of our simple function over x with respect to our measure mu. We call this the Lebesgue integral. We define it as the sum from 1 to n of alpha j times the measure of the preimage of that alpha j. This should say alpha right here. Okay. Why this definition? Well, just think about it for a second. If I have, my simple function, we'll say this right here is a1, this right here is a2, and then this maybe is a3. Okay. Let me just draw an example simple function. I'll say this is here. So alpha 1. This is alpha 2. And then this here is alpha 3. Okay, where does this definition come from? Well, if you look at a simple function, it's just a bunch of, if you just look at the area under the graph of a simple function, what is it? It's just a bunch of rectangles, okay? So what's the area of a rectangle? It's just length times base times height, okay? And like I was talking about earlier, the base depends on the length, if you will, of the base depends on what measure you're picking, okay? So if I want to talk about the area, I'll do it in a different color. The area, what's that going to be? Right? And by area, I just mean this term right here, this integral. Well, let's see, we'll do things backwards. We'll go height times base. Okay, well, what's the height of this rectangle here? Well, it's going to be alpha 2. And then what's the base length? Well, it'll depend on what measure we're picking. Okay, so that's going to be the measure of A1. The measure of A1. Oh, this should be alpha 1. What am I doing? Here. It should be alpha 1. Alpha 1 times the measure of A1. Okay. Let's go to the second one. Well, what do we have? We have a height of alpha 2, and the base set is A2, and the length of A2 is going to be defined by our measure. So we'll have alpha 2 times the measure with respect to mu. Mu is any measure of A2, excuse me. And as you can see quite clearly what we're doing, the last term will be alpha 3 plus the measure of A3. Okay? And we define this guy right here, right? This is going to be what we mean by the integral of the simple function. So you can see where this definition comes from. Now, I don't want to always say, when we talk about, our simple function, non-negative measurable simple function, that's kind of a mouthful, and it will waste a lot of precious seconds. So what I'm going to do from now on is when I say simple function, I mean a non-negative measurable simple function. We're just going to call those simple functions. And you're like, why didn't you say that first? Well, it just makes it maybe a little bit more digestible. I don't know. That's just a guess. Okay. Now, what if I don't want to integrate over my entire space X? What if I just want to consider the integral over a subset? Well, this is actually fairly simple. If E is a subset of X and we just want to integrate over E, what we do is we say that the integral of our non-negative measurable simple function, that'll probably be the last time I say it, or just our simple function S with respect to mu is, okay, same linear combination as in this definition of the Lebesgue integral, but we take each AJ and we intersect it with E. Okay? We take each preimage We take its intersection with E. Okay, we'll do an example here in a moment. So I want to make one more comment. Notice how we call this the Lebesgue integral, but mu is any measure. It's not necessarily the Lebesgue measure. Don't get confused by this, okay? When I say Lebesgue integral, the complete sentence needs to be Lebesgue integral of what over what with respect to what measure. The Lebesgue integral of what function over what set with respect to what measure. Now, if the measure is understood by context, it's just implied, then we might just say, what's the Lebesgue integral of blah, blah, blah. Okay. But don't get confused. When I say Lebesgue integral, that doesn't mean integral of a function with respect to the Lebesgue measure. It just means the integral of a function with respect to a measure. Okay. Okay, now let's look at an example. This is one where you can, Khan Academy style, pause the video, see if you can figure it out. See how much time we have. It's been 31 minutes. We may not do everything in this example. Actually, or maybe we do. There's really no rush. You guys can skip if you get bored. Okay. So this should be a closed endpoint here on the 1. Right here. There should be a closed interval. So let's take A4 as above, right? We're talking about this approximation of x squared right here. And we're taking n is equal to 4. Well, first, let's see. Is A4 a non-negative measurable simple function? Okay, well, I drew it earlier. I drew it earlier. You can obviously see that it was non-negative, right? It was all above the x-axis. Okay. So non-negative, I think you guys can believe me on that. I mean, I did right here, right in front of my face, put the values that it does take on. Okay. Is it measurable? Is it measurable? Well, let's see. We can just inspect it. What is the pre-image of 0? What maps to 0? What you're going to do, you're going to go to the summation and look which characteristic function has a coefficient of 0. Oh, there it is. Okay. So anything in this interval, right, will go to 0. It needs to be in this interval. If it's in any other of these intervals, the characteristic function will be 1. We have a non-zero coefficient, so A4 will be non-zero. So A4 is 0 for x between 0 and 1/4. Is this measurable? Well, let's say we're talking about, well, it depends on the measure, and I didn't specify that here. But let's talk about the Lebesgue measure we just worked with. Is this Lebesgue measurable? Well, if you remember from last video, we talked about how one of the equivalent definitions of Lebesgue measurable sets said that implied that all Borel sets are Lebesgue measurable. And this is a Borel set right here, right? Half open, half closed intervals are Borel sets. So, since this is Borel, this is measurable, and so the pre-image of 0 is measurable. In a similar fashion, the pre-image of 1/16 is this guy right here, is going to be this set. Okay, just look at the coefficient. Just match the coefficient to the characteristic function. Okay, the pre-image of 1/16 is going to be this half open interval, half closed interval right here. This is Borel, this is measurable, so the pre-image of 1/16 is Lebesgue measurable. Same thing with this one, same thing with this one, which again, this should be a right-hand closed interval. All right, so we've shown, or at least talked about, that this is a non-negative and a measurable simple function. Now, let's have some fun. Let's actually compute the Lebesgue integral. Oh, scary. It's actually very simple. All we're going to do is follow the definition. Okay, what did we say this is going to be? Well, let me go back up to this definition. Keep an eye on this down here. Let's see. The integral from 0 to 1 A4 of x with respect to the Lebesgue measure. The Lebesgue integral with respect to the Lebesgue measure. I know it sounds stupid, but we have to be specific. What is this going to be? Well, it's going to be a sum. Okay, well, if you want to know how many terms in the sum you're going to have, just look at the number of characteristic functions. We have 4. Okay, well, so it'll just be from the sum from j is equal to 1 to 4 of alpha j times mu of aj. Well, what are my aj? It is these 4 intervals right here, again, closed. All right. all you're going to do here is we're taking the value of the function, the height, and multiplying it by the length of the preimage of the respective point. Okay, and the length here, we're working with the Lebesgue measure. So our first term in the summation is going to be like this. We're going to have 0 times, what is the length of this interval? Well, it's 1/4 minus 0. That's going to be 1 over 4. And in fact, that's the length of all of these intervals. This is an even subdivision of the unit interval that we have here. Okay, so that's our first term in the summation. That's just going to give us 0. What about the next one? Okay, well, alpha 2, the second term, that's just going to be 1 over 16. That's the height. And then what's the base? It's going to be this set right here. It's going to be the length of this set right here, the Lebesgue measure of this set right here. That's 1/4 to 2. This thing has Lebesgue measure 1/4 right there. Okay, and you just keep going. We're going to have 9/16. The Lebesgue measure of that set is 1/4. And then we're going to have, come on, 1. Lebesgue measure of that set is also 1/4. Okay, that's 0. You can plug this into your calculator and have fun. Well, actually, I have one. Let's do it. We're going to have 1 over 16 times 1 over 4 plus 9 over 16 plus 1/4 plus another 4th. Okay, I get, is this not right? No, that would be awful. 9 over 16 times 4 plus 1 over 4. I get oh, you know what? My left endpoint here is incorrect. So this should actually be this one right here. This is going to be let's see. This is going to be 1/4. My mistake. There we go. 1 over 4. Okay. And that gives me, sorry about that, 1 over 4 squared is 1 over 4. There we go. That gives me 0.328. Okay, so that is the value of this integral, the Lebesgue integral right here. All right, very nice. Just need to change that coefficient. Okay, now we can practice. Let's see, what time is it? All right, it's been 38 minutes. I'll let you compute this and post in the comments what you get. All right, I'm checking to make sure you're paying attention to these videos. I'll do this later. Post in the comments what you get and compare with your classmates, your virtual classmates. Okay, now we're ready to define the Lebesgue integral for a general non-negative function. Now to do so, notice how we had to stipulate that our simple functions were measurable. We're going to do the same thing in talking about the functions we want to integrate. So given any measure space, set X, sigma algebra sigma algebra sigma, and then here we go. Just want to pull this up. Take a measure space X sigma mu, a function from X to a real valued function. We call it measurable. Let me close this, a bit distracting. If the preimage of all intervals, all subsets of R that are intervals of this form, the preimage of those under F is measurable with respect to mu, i.e. this is an element of sigma for every alpha beta and R alpha less than beta. Okay. Now I can swap out this preimage. Instead of considering this kind of interval, I can consider open intervals, closed intervals, arbitrary open or arbitrary closed subsets of R. So what does that mean? I'll get the same definition of a measurable function if, here's another definition. F from x to R is measurable if the preimage of every open subset of R is measurable, or the preimage of every closed subset of R is measurable, or the preimage of every open interval of R, subset of R, is measurable, or the preimage of every closed subinterval of R is measurable. Okay, those are all equivalent to saying that the function is measurable. Okay, now there's some properties. This is what I wanted to pull up here of measurable functions I wanted to talk about, or just look at them. Take some time. We don't have that much time to discuss them today, but they might be useful at one point or another. If you just go on Wikipedia, these things are very helpful. So one thing to notice, this goes for complex valued, it also goes for real valued functions. If I add or multiply measurable functions, they're measurable. If I divide them, as long as the denominator is not 0, I get a measurable function. Okay, you can do arithmetic with them is basically what this is saying. You can compose them. You can take, the supremum, infimum, limit superior, limit inferior, and get measurable functions. You can take the pointwise limit of a sequence and get a measurable functions. Okay, some things to keep in mind, especially if this isn't a review for you. This is you learning the material for the first time. Okay. A side note, and if someone by the name of Young's Measures is watching this, he does geometric measure theory. Maybe he can elaborate on this in the comments if he's watching. It's been 42 minutes. What does a measurable function look like? Okay, because this seems maybe a little, feel like a little bit abstract. Well, they're actually pretty, to some extent, close to continuous functions, if you're trying to get a picture in your head. The technical way of putting it is that and Young's Measures, if you're watching this, please correct me if I'm wrong, a measurable function is what we call approximately continuous. This is an actual term, and that means the set of points where it's not measurable has density 0. Okay, that's just a bunch of, just a bunch of talk for now. I don't know if we'll ever even talk about density in this course. But that's a result from an area of math that, I've read somewhere from an author where he said that fact shows that measurable functions are like continuous, sorta, or continuous enough. Okay, so you don't need to think they're like, it looks like a measurable function. They look like broken TV screens or just something weird and jagged and awful or something. I mean, some of them can be, but if you wanted a picture in your head, that's just if you wanted that. So anyway, to integrate, we're going to take a non-negative measurable function defined on a set x. The Lebesgue integral of f over x, again, specifying with respect to the measure mu, is defined as this. Okay, what is this formula? We're saying that the integral over x of f with respect to mu is the supremum of integrals over simple functions. Okay, so this is the supremum of a set of real numbers. Those real numbers represent the integrals of simple functions, and those simple functions are non-negative. Okay, they're greater than or equal to 0, right, at all points, and they're bounded above by our function f. Okay, and I think, if I'm right, I have an example just to kind of illustrate this to you that I do. Okay, maybe this would have been helpful earlier. So, what does it look like when we're doing this? Okay, well, going back to that example of A4, or an. Where's that? Right here. Okay, ignore this terrible, awful error. This should be 1/4. So this is actually a graph of a sub 4 right now. I have 4 subintervals, right? I'm approximating the parabola x squared on the unit interval going from 0 to 1 by 4 horizontal lines. And I can increase that, okay? I'm going to increase the n in this subscript right here. Watch what happens. Okay. We are getting closer and closer to the shape of x squared. So what this definition is saying, I don't want to mislead you because the simple functions that appear here in this definition can look much different than this, right? This is a really, really nice simple function. The subintervals are uniform and all of that stuff, and there's this equal spacing and all of that. This is slightly misleading because your simple functions are not always going to look like that. Okay, so we just happen to have a nice example. Okay, so keep that in mind. You want to be careful not to get sloppy like I have with some of these coefficients. Okay, but anyway, okay, we're taking the supremum of these integrals. What does that look like? Well, let me turn this on. So here we have the integral, right? This green area represents the integral of this simple function right here for any given n. And what we're saying is, and notice two things here about this green function. I'll turn this off. Okay, this is obviously non-negative, right? None of these horizontal lines go under the x-axis. And it's bounded above by f. None of these horizontal lines goes above the black line, which is the trace of x squared. Okay, and we're saying that the integral of f, the Lebesgue integral of f with respect to our measure, is equal to the supremum of all integrals of simple functions bounded below by 0 and bounded above by f. Why is that intuitive? Well, look what happens, right? Increasing n here is the same, right? This is like taking the supremum, right? It's getting larger and larger and larger and larger, and it's approaching the value of f. Now some of you might say, well, hey, you're just taking a Riemann sum. It's not always going to look like this, right? That's why I'm specifying this is a special case. This is not always going to be the case where you can just divide things nicely up into, subintervals like a Riemann sum, and you get the same as your Lebesgue integral. That's not the case. But I just wanted to show you this is intuitive. Okay? This is extremely intuitive. All right. So, as far as this definition. Okay? So hope that makes sense. Because, now notice how it's the supremum, because the area covered under the curve is always increasing, right? We have some area covered. This covers more area. This covers more area. This even more, even more, even more. We're filling in more and more area as n increases, and we're approaching a least upper bound. Remember, that's the supremum, least upper bound. In this case, for x squared, it's 1/3. But we're going to prove that when it comes to, it's 1/3 with respect to the Lebesgue measure. Okay. All right, so that's the definition. Let's look at an example. Okay. We cannot yet. We need one more fact to, actually evaluate, say, get an equality for a Lebesgue integral. Okay. With respect to the Lebesgue measure. So let's go back to this example. Okay, this approximation, and I didn't add the last term here, so let me go ahead and do that. Now let's use this method of, right down here, this an here, to bound the integral of x squared on the unit interval from below. Okay. And you're like, well, how am I even going to do this? Okay. Well, what is this? This is a supremum, right? This is a Lebesgue integral with respect to the Lebesgue measure. Okay. Integral from 0 to 1 of x squared with respect to the Lebesgue measure. This is a supremum of, oh, come on, of integrals of simple functions between 0 and f. Okay. What does that mean? That means for any simple function, I'm not going to write simple, for any simple function between 0 and f, because this integral is equal to a supremum, that integral of a simple function between 0 and f, well, that's obviously going to be less than the supremum, right? This is the greatest upper bound. So this will be less than the supremum, which is equal to the integral of x squared, the Lebesgue integral of x squared with respect to the Lebesgue measure. Okay. Lots of terms. I hope it's not been too bad you've been able to keep track. Okay, so how do we do this? Well, all we do is just compute the Lebesgue integral, okay, of this simple function, right? Is this a simple function between 0 and x squared? Yes, you can obviously see that that is the case, right? A sub n is in green. This is obviously going to be bounded between the x-axis and our function x squared. So that means that this area is always going to be less than or equal to the actual area under x squared from 0 to 1. Okay? So to bound this from below, all we need to do is compute the integral of this. Very simple. And then we'll do a cool trick at the end. We'll just go ahead and take the limit, right? Because this is increasing, as we talked about. This is an increasing sequence of simple functions. We'll take the limit as n goes to infinity to get a tight lower bound on this Lebesgue integral with respect to the Lebesgue measure. Okay. I'm going to do this a little fast. Well, let's see. We're going on 52 minutes, so I might speed this up a little bit. But I kind of, there's a virtue in being thorough here. Okay. What is this going to be? We can actually do this pretty quickly, okay? We've got our base, which is going to be the length of these intervals, the Lebesgue measure of these intervals, times the height, which is this guy. Okay. I can actually write all this when I take the integral under one sum as follows. I can write the integral from 0 to 1 an of x dm as the following sum. From I goes to 1 to n. Okay. Our height is always going to be f evaluated at the left endpoint. So I have f I minus 1 over n times the length. Okay, this is a uniform subdivision, right? I chose a really convenient example. So this is going to be, let's see, these are all of length 1 over n, all of these. All of these in the sum, again, length, the Lebesgue measure. The Lebesgue measure of all of these sets is 1 over n, okay? So the integral of an for any given n is this right here. Okay. I'm going to go ahead and put the 1 over n outside and take the sum from I, this is bad, I going from 1 to n of I minus 1 over n squared. Okay, and you can put it out here like n cubed. Okay. Squared. Okay. To evaluate this sum, let's see. Well, what are we summing here? Let's see. We're going to have 0 plus 1 plus 2 all the way to n minus 1 squared. And there's a formula for this. You've already been here 54 minutes. I'll go ahead and look it up. It's going to be, I maybe should remember this by heart, This is very unprofessional, right? This is going to be equal to, well, in this case, it's not n, it's I. Okay, this right here, you can look this up. It's just the sum of squares of n natural numbers. This is going to be n minus 1 times n times, we'll say, let's see, I think that'll be 2n, let's see, 2n minus 1. I'm substituting n for n minus 1. That'll be over 6. Okay, so I'm going to get this whole thing. So my integral is equal to, maybe I'll write it like this, n, and my pen does not want to work today, n minus 1, 2n minus 1 over 6. Okay, that is, and then we have that n cubed. So we'll have 6n cubed. You can simplify it. We'll just leave it like that. Save some time writing. Okay, that is the value here. So, right, because this is the integral of f, if it's a primum, we have this bound. Okay, and this is for all, this is for n, any natural number n. This is always going to be less than the Lebesgue integral of x squared with respect to the Lebesgue measure. Okay, so this is the bound for each n. Now the question is, okay, can we, if we pass it to the limit, we'll get, this is an increasing sequence. If we pass it to the limit, we'll get a tight bound, a tight lower bound on the Lebesgue integral of x squared with respect to the Lebesgue measure. Okay, well, let's do that. I'm going to spare you the pain of factoring that. Just look, okay, this is going to be a polynomial of degree 3. The leading coefficient is going to be 2. Okay, so we have a polynomial of degree 3 with a leading coefficient of 2 divided by 6n cubed. That's a degree 3 polynomial. Okay, remember that the limit for your limits of rational functions, the limit when the degrees of the numerator and the denominator are the same is going to be the ratio of the coefficients. Okay, lots of jargon. I'm so sorry. The limit of this, as n goes to infinity, is going to be 2 over 6, which is 1/3. So we get this this is the tightest bound from below. We have this. Now, to get this to equality, we need the monotone convergence theorem, which we'll discuss in the next lecture. But we just have some things I want to finish up. Okay, we're almost done. If you stuck with it this far, good job. You get a pat on the back. Okay, anyway. Now, we've only defined Lebesgue integrals for non-negative functions. For a general function, all we do is we just split it up. So I have another Desmos thing ready. Okay. Let's say I want to integrate, don't even pay attention to all this stuff here. I want to integrate this blue function from 0 to 2. Okay, and this is measurable. Okay, well, we know how to integrate this bit because this is all non-negative. Well, how about this bit? Okay, all we do is we use the fact that we've defined the Lebesgue integral for non-negative functions, and we break things up into two pieces. We first consider the positive part of the function, f plus of x, which is the maximum of f of x in 0. Okay, that's, as you can see, you just look, and so f plus of x is in green here. Okay, it's only considering, it's only drawing f where it's non-negative. Everywhere else, it's 0. Okay, that's the positive part. So we say, okay, I'm going to take what I do when I define the integral of just a general measurable function f, could take positive and negative values. I'm going to integrate over its positive part, and then I'm going to subtract the integral over its negative part. Okay, and that is, okay, what we do to get the negative part of our function f is we draw where it's negative put 0 everywhere else, and then we flip it over the x-axis so that it's a positive function, okay? So as you can see, in purple we have the negative part of x, right? So all we do to compute the Lebesgue integral of f in blue, we take the Lebesgue integral of its positive part and subtract from it the Lebesgue integral of its negative part. And these two are integrals of non-negative measurable functions. Okay, you can check that this is measurable. You can just take it for granted. I'm not going to throw something at you that's non-measurable or anything like that. Okay, or I'll tell you if it is. Okay, and that's how we define the Lebesgue integral for for just general measurable functions. Okay. All right. Just to close this out, I want to talk about these things you have to know when we're going to be working with Lebesgue integrals throughout functional analysis. It's a lot of properties. I'm not going to spend too much time discussing them all. I think they're pretty straightforward. Okay, and they're very similar to what you've seen in calculus. Okay, so I would recommend you write all these down and you know them. Like you should know these like off the top of your head. These are very important to know. Okay, given a measure space, we're going to let E be a subset of X. We're going to let it be a measurable set. So E is an element of sigma, and F and G are just measurable functions defined on X, positive or negative, because we've now defined the Lebesgue integral with respect to a measure for general measurable functions. First of all, it's monotone. If f is less than or equal to g, then obviously its integral with respect to the measure mu should be less than the integral of g with respect to the measure mu. Okay, these are all things you can prove. This would actually make a great exercise, especially if you're new to this. These things follow from the definitions. Also, let's say just fix a non-negative measurable function f. If I integrate f over a, and then I integrate it over a bigger set, right, I should obviously get a bigger number integrating over a bigger set. So we have monotonicity with sets. Okay, linearity, integrals distribute across, right, the Lebesgue integral distributes across addition and scalar multiplication. Again, you can prove all these things. If I take the Lebesgue integral of a zero function, of just if f is 0, then its integral should obviously be 0. And that includes even if the measure of my space is infinite. This should be x right here. Okay, if the measure of E is infinite, even if that's the case, the integral is still 0. And that's taking the convention. This requires we take the convention that 0 times infinity is equal to 0. If the measure of my set is 0, then the Lebesgue integral of my function over that set is 0. All right, so the Lebesgue integral of a function over a set of measure 0 is 0, even if that function is just infinity. Again, to prove this requires we adopt the convention that 0 times infinity is 0. Okay. If f is non-negative, then we can rewrite, okay, E is a subset of x, we can rewrite the integral of f over that subset of x, E, the Lebesgue integral, as just the integral, the integral over the entire space x of the function of the characteristic function of E times f. Right? You can kind of see why this is the case. This function is 0 except on E. Okay, and when we're on E, we just have the integral of f. Okay. If f is non-negative and the integral of f over E, the Lebesgue integral of f over E is 0, then f is equal to 0, but it's not, it doesn't mean it's always 0 for every single x. It's just 0 almost everywhere with respect to mu. Okay, so if the Lebesgue integral of f over a set is 0, then the points where f is not 0 when evaluated has mu measure 0. And we talked about what that meant in the previous lecture. Finally, property 8. If f is equal to g mu almost everywhere on a set E, then the Lebesgue integral of f with respect to mu is equal to the Lebesgue integral of g with respect to mu. Okay, again, what does it mean when I say f is equal to g, mu almost everywhere? That means the points where f and g differ form a set of mu measure 0. Okay? All right, guys, that's it. Next, we have one more sort of big lecture on measure theory, big grand lecture on the monotone and dominated convergence theorems. That will be coming probably later this week if I can get to it. Then it's complex analysis, and then it's functional analysis. If you spotted any errors or anything like that, please leave in the comments. Trying my best just getting back into this, so appreciate all of you for watching if you stuck through it this long, and I'll see you all in the next video.